In the earlier sections, we have learned union, intersection, and difference of two sets. In this section, we will go through some practical problems related to our daily life. Welcome again to Mathematics of Engineering. The first formula involving operations of sets, union, intersection, and difference follow two conditions. First, that sets A and B are finite sets and they have no intersection. The formula is then given as the cardinal number of the union of two sets would be equal to the number of elements in the first set plus those in the second set. Suppose we have set A with the elements 6, 7, and 9, and set B with the elements 1, 4, 5, and 10. Studying the sets with exact elements, we can conclude that A and B are finite sets, and analyzing the elements, there isn't any common element between the sets. Taking the union of the sets will yield the elements 1, 4, 5, 6, 7, 9, and 10. The cardinal number of which is 7, which is equal to that of set A with 3 elements and B with 4 elements. The second formula still focuses on the condition that the two sets are finite, but in this case, there are some common elements. The formula provided is the cardinal number of the union of two sets A and B is equal to the number of elements of each set A and B less the number of elements in their intersection. With the following example, set A with 1, 2, 6, 7, and 9 has 5 elements, and set B with 1, 2, 4, 5, 10, and 12 has 6 elements. Furthermore, the elements 1 and 2 are common in both sets. Substituting the values in the formula will show that the union of sets will have 9 elements, which is equal to the cardinal number of elements of each set less their intersection. The third formula covers 3 sets in the analysis, and these sets are considered finite. The third formula states that the number of elements in the union of the 3 sets, A, B, and C, would be equal to the number of elements in each individual set, less than the number of elements in the intersection of 2 sets, and add the number of elements contained in the intersection of all 3. To prove this formula, we start with the analysis that the number of elements in the union of the 3 sets would be the number of elements in set A plus that of the union of sets B and C, less the number from the intersection of A with the union of B and C. By expanding the second term, n of the intersection of B and C can be seen as the number of elements of each individual set less their intersection as stated in the second identity. Next, we focus on the third term. Remember the distributive property of intersection that states the intersection of A with the union of B and C would be equal to the union of the intersections of sets A and B and A and C. If we include the cardinal number in the equation, we get the cardinal number of the intersections of A and B and A and C less the number of elements in their intersection. And lastly, to revert back from the distributive property, we get n of the intersection of A and B plus n of the intersection of A and C less n of the intersection of the 3 sets. Thus, we arrive at the same identity. Check the first example. If x and y are 2 sets such that the union of x and y has 50 elements, x has 28 elements, and y has 32 elements. How many elements does the intersection of x and y have? From the given, we have n of the union of x and y as 50, n of x as 28, and n of y as 32. Analyze that the problem discussed common elements in both sets, so the second identity is to be applied, which states that n of the union of the sets are the n of the individual sets less the n of their intersection. By placing the intersection of x and y to the left side as it is the unknown, we get 28 plus 32 less 50, which is equal to 10. The next example states, in a school, there are 20 teachers who teach mathematics or physics. Of these, 12 teach mathematics and 4 teach both physics and mathematics. How many teach physics? In the statement of the problem, the word or gives us a clue of union and the word and gives us a clue of intersection. Express the given as n of the union of m and p as 20, n of m as 12, and n of the intersection of m and p as 4, assuming the m stands for mathematics and p for physics. Again, using the second identity formula, we can extract n of p as n of the union of m and p less the n of m plus the n of the intersection of m and p, which yields 20 less 12 plus 4, resulting to 12 as the number of physics teachers. Another example states, a college awarded 38 medals in football, 15 medals in basketball, and 20 in cricket. If these medals went to a total of 58 men and only 3 men got medals in all the 3 sports, how many received medals in exactly 2 of the 3 sports? From the given, n of the union of the 3 sets is 58, n of football is 38, the n of basketball is 15, and the n of cricket is 20. Additionally, the n of the intersection of the 3 sets is 3. Using the third formula, the unknowns would be distinguished as the n of the intersection of 2 of the sets less their intersection. We solve for the intersection of all the pair of sets first by plugging the values for the other terms, and we come out with 38 plus 15 plus 20 plus 3 less 58, giving the answer 18. Take note that the result includes the intersection of all the 3 sets, which was given as 3. So, by deducting the intersection 3 times, we get the value 9, which is the number of athletes who won 2 winning sports.